From our past discussion, we are already done with your saturated hydrocarbons, particularly your alkanes and cycloalkanes. For our discussion in this video, we are now going to move forward with our unsaturated, meaning we do not have the maximum hydrogens that your carbon is capable of bonding with. So of course, for instance, we have your alkenes and alkynes. Remember class, alkenes and alkynes are unsaturated hydrocarbons. And this structural feature actually gives them their distinct bonding characteristic, of course, their unique naming rules according to IUPAC, physical properties, and lastly, their chemical reactivity. So comparing your unsaturated hydrocarbons to your alkanes, your saturated hydrocarbons, they are usually more reactive because your double and triple bonds are actually electron rich. Our class, again, for this video, let's start discussing first alkenes. Ayan. So remember, our alkenes actually have many applications in the industry. For instance, it is used as raw material for plastics and polymers. Diba? Remember, your ethene are actually precursor for our PET or polyethylene bottles. Okay. Secondly, it also acts as a precursor or sometimes intermediate in pharmaceuticals, particularly in drug synthesis. Okay. And then thirdly, agriculture and polymer industry in the production of your PVC. Diba familiar? Your PVC pipes, your Teflon tubes, and other synthetic rubbers, again, through polymerization reaction. And last two, don't forget, again, for the textile industry, we can use or we can produce synthetic fibers through the polymerization of your propene in order to produce polypropylene fibers. And lastly, currently this is the topic or the main highlight of some green chemistry research. So again, your alkenes are the basis for biodegradable plastics bio-based ethene compounds. So again, that's just the application, one of the many applications of your alkenes. So let's proceed with our structural features and properties of alkenes. Class, remember, our keyword here is the presence of carbon-carbon double bond, at least one for your alkenes, okay? For the structure, again, it is a prerequisite or it is required that in its structure, it has at least one carbon-carbon double bond. And remember, from our discussion, in your hybridization, typically alkene adopts the sp2 hybridization. Remember, we have one pi bond in its structure and the remaining bonds are 3 sigma bonds. All right, for examples, remember, the bond angle is 120 degrees and the molecular geometry is trigonal planar around your double bond. Class, again, no need to memorize our general formula, but for your acyclic alkenes, remember, its general formula is CnH2 sub n. It's just like the same with our cycloalkane. So for instance, ethene, a 2-carbon alkene, and propene, a 3-carbon alkene. All right. So here in our discussion, you also need to know the degree of unsaturation. So later on, I will give you the formula in order to compute for the degree of unsaturation. Because class, remember, alkenes are unsaturated compounds. Okay. So class, in its formal definition, your Du, which is somehow abbreviated or symbolized with your raw Greek symbol, ayan, it indicates the number of pi bonds, first one. Second, the rings present in your molecule. Also, what is the relevance of your Du in our discussion? Class, it helps us predict or determine the level of unsaturation or in other words, hydrogen deficiency in reference to your saturated hydrocarbon alkane. Okay? So again, later we will discuss this in particular, the formula. So we have technicalities kasi here, class, because each double bond actually or ring, we will count it as one in our computation. Or remember, for your Du, we have a particular formula. So no need to stress out this early for our particular example here. Clear? Again, for our next feature, for your nomenclature class, similar with our discussion on your IUPAC naming, your alkene is actually least prioritized, diba? Again, alkene, alkyne, alkane. Ayan, they are in the last end of our prioritization list. But in more specifically, you need to identify the longest chain with your carbon-carbon double bond included in that longest chain. And remember, for the suffix, we will add E and E. And class, aside from that, take note that we need to position your carbon-carbon double bond at the lowest possible number of carbon. All right? So remember, we also discussed the common names in general of your organic compound because they are often derived from trivial names. So for instance, ethylene is the common name, but in your IUPAC nomenclature, it's just your ethene. All right? So class, usually, their common names are actually their old names. Okay? For instance, propylene, ayan, IUPAC name is propene. Okay? So class, remember in the board exam, they can interchange the names of your organic compounds. They can use the common name. They can also use the IUPAC naming. So that's why you need to familiarize yourselves with our prominent examples of your common trivial names for our list of organic compounds. Clear? So going back, our next feature is the geometric isomerism. Class, remember in our discussion on our stereoisomerism, again, your geometric isomerism is exclusive for your alkenes, particularly in our double bonds. So in your geometric isomerism, we have two types, and we will discuss this in detail after our discussion on structural feature. Class, I think you are familiar with the cis-trans and easy or Entgigen and Zusamen isomerism. All right? So later again, we will emphasize more on this, but for now, let's move forward for our physical properties. So for boiling point, check. Your alkenes have generally slightly lower boiling point than their corresponding alkanes. And that's because of the geometric isomerism. Okay? Again, due to your similar molecular weights, but they have less compact structures due to the presence of your double bond that exists in cis or trans isomerism. And lastly, for the solubility, or remember, alkenes or in general organic compounds, they are soluble in nonpolar organic solvents because class hydrocarbons are relatively nonpolar. Okay? So that's why, as a result, they are also water insoluble. Class, that's it for our structural features for your alkenes. Now, let's proceed with our formula for your Du. So class, I think This is only the sole formula that you only need to memorize here in your core chem. Again, we are heavily concept-based here, but for the sake of our discussion on alkenes, or particularly for unsaturated compounds, those that contain double or triple bond, you need to predict the unsaturation or the hydrogen deficiency. Again, that's just synonymous, degree of unsaturation or the level of hydrogen deficiency. So again, class, as I have emphasized earlier, it is depicted by your raw symbol or raw Greek symbol. So for our formula, pretty straightforward. We have 2 plus 2 carbons. Again, you need to multiply by 2 the number of carbons in your structure minus H, the number of H's, plus the number of nitrogen atoms minus the number of your halides or halogen atoms all over 2, or divided by 2. Okay? So remember, class, for our interpretation here, if you have a raw or an unsaturation equal to 0, that means you don't have a double bond or a ring or a triple bond in its structure. So sir, meaning fully saturated yung compound if your Du is equal to 0. Correct. Okay? Class, when your Du is equal to 1 naman, either you have one double bond or one ring. Again, it's either or, not and. Okay? Again, either one double bond or one ring is present in your structure. Alright? O sir, how about if Du is equal to 2? Let's check. For your Du equal to 2, either we have one double bond and one ring, or two double bonds or two rings. Again, class, for your double bond, we count it as 1 Du. For your ring, we also count it as 1 Du. And lastly, for your triple bond, we count it as 2 degree of unsaturation. That's why, if you have a Du of 2, it can also mean that you have one triple bond in its structure. Sir, do we need to memorize the formula? Yes na yes, class. Okay? So class, again, in the board exam, this usually appear as a straightforward question. Again, formula based, you are going to ask about the Du of a certain molecule. So class, in interpreting these again, for your double bond or ring, it is equivalent to 1 Du, and for your triple bond, equal to 2 Du. Clear? Ayan. So class, again, that's one of the properties of your unsaturated compounds. Now, let's go to a more specific properties of your alkenes. Starting with cis-trans isomerism. At this point, we are now going to enter your isomerism discussion. So somehow, class, some students are intimidated with this discussion. But don't worry, in the board exam, it's just as easy, di ba? As easy peasy. Let's proceed. Ayan, for your cis-trans isomerism, again, your cis-trans isomers occurs when each carbon of the double bond is bonded to different groups, while the easy system, we will discuss it later, okay? Again, class, this one is a cis isomer because, okay, your identical groups or similar groups are bonded on the same side. Ayan, again, here is your two identical groups. So again, you need to cut your double bond by this way. For cis isomer, two identical or similar groups are on the same side of the double bond, okay? Class, again, this is your line angle structure. I'm sorry, this is your expanded structure, and this one is your ball and stick model. All right. So again, for the trans isomer naman, if you cut your double bond, and then, of course, your identical substituents are on the opposite sides of the double bond, that is your trans isomerism. Okay. So again, in terms of our boiling point and melting point, they are heavily affected by intermolecular forces of attraction in your alkene structure. Class, let's discuss this briefly. For your boiling point, if your molecule is highly polar, meaning for your cis, this is highly polar because your similar substituents are on the same side, they will have higher boiling point. Okay? So for the melting point naman, if your alkene is highly symmetrical, again, it will have higher melting point. So similar with this one, class, even though it has higher boiling point, because of the symmetry with this plane of symmetry, again, it will have higher melting point. Sir, why do symmetry increases the melting point of your organic compounds? Class, because when your compound is symmetric, your molecules pack more efficiently in the solid state. Again, when they are highly symmetrical, for instance, here in our example, they can align in a well-ordered, tightly packed solid crystal structure. And this strong regular packing will lead to a more stronger intermolecular forces. And as a result, class, more energy is needed in order to disrupt or break this IMFA. Okay? So class, again, for our physical properties, for your highly polar molecule, increase boiling point, and for highly symmetrical alkene structures, increase melting point. Okay? So I hope it's clear. Again, for your BP and MP, they are directly proportional with polarity and symmetrical or symmetry of our alkenes structure. Now let's proceed with our easy isomerism. Let's check. Okay, so class, here in our discussion on easy isomerism, di ba recall, we already discussed your Kahn and Gold pre-log rules. Because here, class, in determining your E and Z isomers, we need to apply the concept of your CIP rules. Okay? So again, let's just discuss first the two types of E and Z isomerism. First one, for your Z, it literally translates to zusammen, meaning together or in a group. Here, your higher priority groups, based on your CIP rules, di ba, remember your A's, assign, compare, expand, are on the same side of the double bond. For your E or E isomer and vegan, your higher priority groups are on the opposite sides of your double bond. So class, somehow, your cis-trans and easy isomerism have similarities, but easy are very particular in using your CIP rules. For our easy determination, we will also cut the double bond in half, okay? Again, for this one, we will now use your CIP rules in order to prioritize the groups on the double bond. Let's check, ha. This one, again, is your Z isomer, okay? And this one is your E isomer. Class, here I have a tip. When you say Z, they are on the same side, okay? For E, they are opposite or opposite of each other. Let's double check. This one is Z because based on CIP rules, your CH3 for these two substituents are prioritized. Okay, so this is your first priority, and between Cl and H, which is highly prioritized, diba? Cl or chlorine atom has a more or has a higher atomic number. That's why your highly prioritized atoms are on the same side of your double bond. Okay, so I hope it's clear. For your E opposite because your CH3 and your Cl, based on your CIP rules, ayan, they are on the opposite side. Okay, so class, in order to test your knowledge here in your easy isomerism, let's try answering our sample problems here. Check. Ayan, very easy. Label each carbon-carbon double bond as E and Z isomerism. First structure, class again, divide first your double bond into two and then apply the CIP rules, is assign, compare, expand. Remember, first with your first carbon here at the left, which is highly prioritized. Our first atom here is carbon or hydrogen. So obviously, you are C. So that's why we will prioritize methyl group, okay? For our right carbon here, which is highly prioritized, chlorine or bromine. Class, use the step 1, assign based on the higher priority with your higher atomic number atom. Remember, bromine has a higher atomic number compared to chlorine. That's why this is our priority atom. Sir, parang opposite sila. Yes, that's a good observation because our answer here is E. Okay, on next structure, ayan. First strategy again is to divide the double bond. Analyze the left carbon, analyze the right carbon and their respective substituent. Class, for the left carbon, C. This is the priority functional group because again of your carbon atom as our first atom in comparison with your hydrogen. For our right carbon, again, ang first point of difference nila in our second step, diba? Assign, compare the first point of difference. For our fourth atom here, we have H, as you can see here. For our fourth atom here, check, we have your C. And remember, we prioritize carbon atom in comparison with H because it has higher atomic number. Sir, answer is same. Of course, that is your Z isomer. Alright? Class, last example here. Ayan, of course, here, we have now two different isomerism. The first one is here, and of course, the second one, sorry, is here because we have two different alkene functional groups. Class, assign whether it is a Z or E isomer. Let's check. Class, please pause the video, ha. Try answering your sample problems. Now, I will discuss the answer here. For our double bond here, remember, we have a hydrogen attached because this one is a line angle structural formula. Between C and H, we will prioritize your phenyl functional group. Again, class, C6H5 is just an aromatic ring, okay? For the next carbon, again, we have H bonded directly to your carbon, which is doubly bonded to another carbon. Between this functional group and your functional group here, hydrogen, of course, we will prioritize your cyclic ring structure. So that's why this is categorized as E opposite, okay? And class, lastly, ayan. Again, we have another double bond here, assign whether it is E or Z isomer. For the left carbon, of course, this one class is just CH3 substituent. And comparing it with our cyclic ring structure here, of course, we will prioritize this functional group, okay? And for the right carbon, class, again, we have an imaginary H directly bonded to your carbon doubly bonded carbon. Sir, I know that's same side because we will prioritize your carbonyl carbon. Plus, that's a correct observation, okay? So again, you need to heavily use your CIP or Kahn-Ingold pre-log rules in order to determine whether your alkene or double bond is in E or Z configuration. All right, we are done with our discussion on isomerism. So with that, let's proceed with the other features of your alkene functional group, starting with your properties of your carbon-carbon double bond. Ayan, so class, first important property to note is the restricted rotation in your CC double bond. So again, your rotation, unlike your alkanes, is restricted here, and it can only occur if your pi bond breaks and then reforms. So usually this is in your transition state. When you form or when you break your pi bond and your sigma bond is the only stabilizing bond between your carbon-carbon bond. So again, class, this process is particularly unfavorable because it needs a large energy in order to proceed with your pi bond breakage. Okay? Next. Again, we discussed this, stereoisomerism, particularly your diastereomers can also form aside from your cis trans and easy isomerism. Sir, how will diastereomer form here in your CC double bond? Again, it will form when two groups on each end of your CC double bond are different from each other, okay? So usually class diastereomeric forms are rare for your alkenes. So for our discussion, don't worry, you only need to remember cis trans and easy isomerism. So again, this one is just supplementary feature of your carbon-carbon double bond, okay? And lastly, for the stability, trans alkenes are more stable than cis alkene. Class again, trans isomer or your E isomer are generally more stable than their cis or Z counterpart due to reduced steric hindrance. Very obvious because in cis or your Z isomer, your two bulky substituents have repulsive forces. Again, in order to predict the stability, as you increase the number of R group in your alkene functional group, here is our summarization. The stability of an alkene increases as the number of R group on the C double bond C increases. And that's because of the increased IMFA in your alkene's carbon skeleton. Okay? So again, class, in terms of the stability, 1-butene, because it is a terminal alkene, is relatively unstable compared to your cis-2-butene and trans-2-butene. Comparing cis and trans, again, much more stable ang trans because your repulsive, okay? Repulsive substituents are on the opposite sides. Okay, so class, that's it for the properties. Let's proceed with the chemical reactivity. Keyword here, your alkenes actually are highly reactive and their main mode of reactivity is through electrophilic addition. So literally, you will add an electrophile in your double bond. Sir, what's the reason? Plus, remember, from our discussion of hybridization, the pi bonds originating from the unhybridized p orbital are actually rich in electron. Diba? We have 4 valence electrons available in your double bonds found in our alkenes. That's why its tendency is to attack or abstract an electrophile and to add it in its structure. So usually class, we form a positively charged intermediate, or we call it your carbocation. Ayan, remember, your electrophilic addition occurs through formation of transition state. Diba? In our discussion ng reaction mechanism, transition state are your sites of your high energy intermediate. So remember, carbocation is highly reactive and high in energy, or synonymously unstable po. Okay? So don't forget that class again, your electron-rich molecule is always the first to attack for your electron-poor molecule. Okay, again class, the reverse process will not occur. Always the electron-rich will initiate the attack to your electron poor or electrophile molecule. Okay? Again, we will see a lot of electrophilic addition of your alkenes. I think ma-overwhelm kayo, class, and you need to familiarize with those electrophilic addition mechanisms. Class, next. Here, in your chemical reactivity, we have a typical rule. I think you are familiar with this, your Markovnikov rule in adding your electrophile. Okay? Let's proceed discussing your Markovnikov addition. Ayan. Class, please recall. For Markovnikov rule, of course, for instance, you have your hydrohalogenation. Familiar? We use simply your HX, wherein your X is a halogen, and we add it to your alkene. So, of course, with your Markovnikov rule, your H or your hydrogen, ayan, will bond to the less substituted C, or your carbon that has more hydrogen to begin with. For instance, class, please try answering this one. We have your HBr molecule, and based on your Markovnikov addition, again, it will add to your less substituted C, or that carbon that is doubly bonded to another carbon that has more hydrogen to begin with. So again, it's either this carbon or this carbon only. Again, less substituted. Again, this is your particular carbon. Okay, so again, class, for Markovnikov addition, the site of binding of your H coming from your HBr will be your less substituted C, and here we will form a tertiary carbocation. That's why we prefer adding your hydrogen to your less substituted C. Okay? Again, for Markovnikov addition, these are regiospecific reaction when there is only one of two possible orientations of addition that occurs. So again, very important si Markovnikov's rule in predicting whether your H will add to the carbon with fewer alkyl substituents or not. Okay? So again, class, most of the time, your electrophilic addition follows your Markovnikov addition. Oh, sir, what is the anti-Markovnikov addition? So class, your hydrogen now will add to your more substituted carbon. Let's see. Particularly for a certain reaction of your alkenes, your hydroboration oxidation, we will discuss this later. Your H now will bond to your more substituted C or has less hydrogen to begin with. Sir, what is the carbon, class? This is your carbon that is more substituted because it is bonded to two different carbons, particularly methyl groups. Okay? And clearly, class, wala nga siyang H in its structure. And that's why we call it your anti-Markovnikov addition, the opposite mechanism of your Markovnikov addition. Here again, the addition of your electrophile follows the opposite pattern with respect to your Markovnikov rule. So usually, class, for anti-Markovnikov, we use ROOR molecule, just like your hydrogen peroxide. So I know you are familiar with peroxide effect. For instance, sa hydroboration oxidation, we use hydrogen peroxide. That's why it induces anti-Markovnikov rule. Okay, so again, our carbocation intermediate now is relatively unstable compared to your tertiary carbocation that can be produced in your Markovnikov addition. Okay, class, don't forget the difference between your Markovnikov and anti-Markovnikov addition. Clear? Next process or feature is with our specific type of electrophilic addition. We have the syn addition and anti addition. Let's discuss. For syn addition, literally, class, our keyword here is your substituents coming from our reagents will add to the same side of your double bond or on the top face, same top face or same bottom face. So what's the product here? Because they add on the same side, di ba recall, you will produce a very regiospecific product that is in cis arrangement. On the other hand, for anti-addition or anti-addition, from the name itself, anti, opposite sides, of course, the product is regiospecific, you will only yield trans product. Okay? Sir, do you have a figure here to visualize syn and anti-addition? Let's check. Ayan, for instance, you have here your particular alkene. Upon electrophilic addition, for syn addition, your two new substituents will add on the same side, particularly at the top face, and this one, we call this your syn addition. So class, again, it can either be at the top face or at the bottom face. Alright? Again, our only requirement here is that they will add at the same side. Okay, it depends kasi class on the substituents on your original molecule. For your anti-addition, again, they will add at the opposite side. So usually, class, this is the addition mechanism for your bromine or halogens in general due to their bulky molecule. Okay, remember, for anti-addition, this is usually adopted by your bulky substituents being added in our carbon-carbon double bond. Again, opposite side po ang point of attachment ng new substituents natin here. For syn addition, cis ang product. For anti-addition, trans ang product natin. Clear? Class, we are done with the features with our last topic here, carbocation stability. Again, class, your carbocation, depending on their stability, we heavily rely on the point of attachment of your mainly positively charged carbon. Okay? So again, your many alkene reactions proceed via formation of your intermediates. So usually, class, as I have discussed earlier, through formation of carbocation intermediates. And these intermediates can actually be affected by their stability. Okay? The stability greatly influences, on the other hand, the reaction pathways first, the regioselectivity, and lastly, very important to, possible rearrangements in order to form a more stable carbocation intermediate. Class, in your manual, check. We have enumerated your particular type of intermediate or carbocation intermediate in particular and in their increasing stability. See, again, class, you need to remember this. That's why, ayan, we have a mnemonics here, don't worry. Let's see. Viral memes put stand accounts beyond trends. Again, viral memes put stand accounts beyond trends. Let's check. Again, this is increasing stability. Okay? Sa class, vinyl or vinylic cation. Familiar with the term vinylic? Again, that's the time when your positively charged carbon directly participates in double bond formation. Okay? So again, this is relatively unstable because of the electron withdrawing property of your double bond. Next, methyl cation. Again, this is just a particular carbocation that is relatively unstable because your carbon is only bonded to your 3 hydrogen atoms. Next, Primary carbocation because it is bonded to one R group. Secondary for stun, bonded to two different R groups. Allylic cation for accounts of class. Again, your allylic cation now, the positively charged carbon, is bonded to your carbon that participates in double bond formation. It is not directly bonded, okay? That's why class, relatively stable to because of the electron-rich nature of your double bonds. Next, for our B beyond, benzyl, and lastly, trans, tertiary class, ang ating very stable carbocation because your carbon is connected to electron-donating groups, okay? And that stabilizes your structure of our carbocation intermediates. Clear? Again, class, don't forget this, viral memes, put stand accounts beyond trends. Ayan, class, that's it for the requirements or the features that you need to know in order for me to discuss our electrophilic addition. Class, now, we will now proceed with your electrophilic addition, the characteristic chemical reactivity of your alkenes, wherein your electron-rich double bond will attack an electron-poor electrophile in order to add your electrophile to your alkene structure. I know, medyo saturated na kayo, so you can pause the video, take mini breaks, comfort room break, or snack break. But for me, class, I will proceed with our discussion on electrophilic addition. This one, class, we will discuss this in detail, our 6 electrophilic addition reactions of alkene. You need to remember, class, the features of the 6 electrophilic addition. So let's start with hydrohalogenation. Ayan, for your hydrohalogenation, key features, again, we will produce intermediate here, particularly carbocation. And that's why it's a two-step reaction. So most of the time, class, our electrophilic addition occurs through the production of your carbocation intermediates, okay? In order for your rearrangement to occur. So here, remember, our key features, it follows Markovnikov rule, and it proceeds either via syn and anti-additions. Okay, class, again, it is not that regio-selective because it can either proceed with syn or anti-addition. Let's check. For your alkene, for hydrohalogenation, from the name itself, hydrogen and halogen. Okay, we will add these two different substituents to your double bonds. Let's check our particular reaction mechanism here. So for arrow pushing, remember, your electron rich will be the one to initiate an attack and it will obstruct your proton via the Markovnikov rule. Again, it will be on your less substituted carbon. Okay, so don't forget that, class. For your Markovnikov rule, your hydrohalogenation will follow that in order to produce this highly stable intermediate. Okay, clear ba? For the step 2, ayan, nucleophilic attack na po ng bromine atom. So class, for the addition of your, ayan, halogen, we will follow syn or anti-addition. Again, class, it depends on the steric hindrance available or present in your structure. Okay, so what's the product of hydrohalogenation? C. This is one of the strategy in order to form alkyl halides. Class, in order to visualize clearly our hydrohalogenation, let's watch this short animation. See, again, it follows Markovnikov rule. So hydrogen will attach to your less substituted carbon. Ayan, or it has more hydrogen, as you can see. And then this is your electrophilic addition. The step 2, ayan, we will add now your bromine atom. Okay, so class, again, ayan. For our second step, your bromine will be added in your electrophilic addition. Again, for the first step, that's your nucleophilic attack. Second step, electrophilic addition. Okay, class, let's proceed with our next reaction, halogenation. Class, this one naman, still two-step reaction, but instead of forming your carbocation, C, it proceeds via formation of your bridged halonium ion intermediate because it follows anti-additions, but strict follower po yan ng Markovnikov rule. Let's see from your manual. This is the general summary. Again, this is just simple addition of 2 halogens in our or across the double bond, one here and one here. Class, our product here is vicinal dihalide. When we say vicinal, your new products attached to 2 adjacent carbon. Okay, so again, let's check the mechanism here. First step, similar with your hydrohalogenation, it will follow your Markovnikov rule. But this one, class, we will form your bridge halonium intermediate. So this one is very important because your bromine, or particularly or in general, your halides or halogen, they exist as diatomic molecule and they are relatively bulky. Okay, again, because of that, they will adapt your bridge halonium intermediate cyclic ring structure in order to have a highly reactive intermediate. So again, that's the electrophilic addition. And then lastly, nucleophilic attack, wherein it will follow anti-addition. Ayan, class, our product here is a vicinal dihalide. Okay, so in order to visualize this more clearly, let's watch this short animation. Okay, so class, ayan, so let's check our animation here. Diba? First one, again, is your nucleophilic attack forming this bridged halonium intermediate, and then the last halogen atom will be added through your electrophilic addition. Okay, so class, again, don't forget our particular halogenation reaction, wherein you will form your vicinal dihalide. Class, again, I would like to clarify, dapat wala na yung positive sign here, okay? Again, that's your halogenation. And actually, class, your halogenation is very important in your laboratory for unknown analysis of your functional group or organic compounds. Diba? I hope you had or you experienced your unknown analysis in your OrChem lab class. For our Did You Know segment, ayan, we have here your bromination reaction. So did you know? Ayan, red no more. Again, the color of bromine or your diatomic bromine is red. For bromine test, we use this in order to produce, ayan, a vicinal dihalide through halogenation with this following specific reaction. So class, again, originally in the solution, you will add first your alkene organic compound. Okay? So pag present si alkene, your bromine will retain the color red, characteristic color of your bromine. But if you have an alkene found in your solution, ayan, madadecolorize siya or it will be indicated by the disappearance of bromine's red color because class, it's successfully added to your alkene through electrophilic addition with this structure. Okay, again, bromination is a type of your halogenation wherein we will add your bromines in our or across our double bonds. At last, let's check the specific example of our bromination experiment.
Hi, I'm Abby, and I'm a graduate student in Gym Lab, and today we're going to be doing a demonstration on bromination of alkenes. So, if you look at this test tube, we have three different chemicals. So in this test tube we have hexane, in this test tube we have cyclohexene, and in this test tube we have toluene. Now they're all colorless and clear, but we have one that's alkane, one that's alkene, and one that's aromatic.
Class again don't forget their functional groupings, okay? Cyclohexane, alkane. Cyclohexene, a type of alkene. Toluene, even though it has double bond because of the aromatic ring structure, it is under aromatic compounds. Let's check the particular reaction that will occur upon addition of bromine.
We're going to be adding bromine in dichloromethane, which is kind of brownish red solution, and if the bromine reacts, then the red color will go away. So anything that remains red is unreacted bromine. So let's start by adding the bromine to the hexane. So we still have this orange solution, which means bromine is still in there. Now we'll add it to the cyclohexene. And you can see, upon addition, the orange color goes away. We can show you that one more time. We're going to be adding bromine in dichloromethane, which is this kind of brownish red solution. And if the bromine reacts, then the red color will go away. So anything that remains red has unreacted bromine in it. So let's start by adding the bromine to the hexane. So we still have this orange red solution.
Class, diba? Amazing. Remember, cyclohexane po is generally unreactive. Your alkenes are unreactive to bromination. Let's continue the video.
And the color goes away. Now for toluene, we still see the bright red color. So what we're seeing here is that the bromine is reacting only with the cyclohexene, not with the cyclohexane or the toluene. And the color goes away. Now for the toluene, we still see.
Alright, so class, remember, even though your toluene has a double bond, because of your aromatic ring structure, its double bond is participating in electron delocalization. That's why it is not reactive to your bromination. Again, stable po ang aromatic ring structure, okay? Class, let's continue our discussion with our next reaction. Ayan, so for our next reaction, we have hydration. Class, this one is a very unique, okay? Unique reaction because it's a three-step reaction. So don't worry, class, for the board exam naman, usually you only need to see the pattern on our different electrophilic addition reactions. Let's check our general reaction mechanism. Again, your features here are just similar with hydrohalogenation, okay? So again, it will follow Markovnikov rule, wherein we will add your electrophile to our pi bond. And class, your carbocation rearrangement, careful, can also be, okay? Can also be occurring in our transition state. And lastly, this can occur either syn and anti-addition. So let's check the specific mechanisms here. Ayan, for your hydration, for instance, we have your water in an acid catalyzed reaction. Again, class, you need an acid here in order to proceed with hydration. So here we have your, what's this? Cyclohexane. And of course, electrophilic addition, again, your double bond, electron rich, will abstract a proton coming from your water. And this will be our intermediate. Okay, that's the first reaction. The second reaction, again, another water molecule, because of the electronegativity of your oxygen in its structure, it will attack the carbocation produced upon electrophilic addition in order to produce our second intermediate here, wherein your oxygen will carry a positive charge. Class, this one is a highly reactive intermediate. Again, unstable po si oxygen that carries a positive charge because remember, oxygen is electronegative. That's the second reaction. For the third reaction, check. Finally, we will now yield your alcohol product through, okay, through the abstraction or the reaction of your water, particularly its oxygen, that will attack your proton with our intermediate here. Okay? So again, our general product here, class Markovnikov rule, usually addition lang ng H2O across the double bond. So if it's Markovnikov, again, your hydroxyl group will attach to your, again, more stable carbocation. That's why this is the point of attachment. In order to produce a highly stable alcohol. This one, class, is a primary alcohol. Okay? Don't forget that. Again, for hydration, unique is your three-step reaction. Again, that's the unique characteristic of hydration. Clear? For our next reaction, we have halohydrin formation. Class, remember, halohydrin formation, it is similar to the mechanism we have seen in halogenation. So, sir, does that mean that we will also form bridged halonium intermediate here? Yes. And this reaction is also a three-step reaction. As you can see here, this is our general reaction mechanism in order to form your halohydrin. Class, from the name of your reaction itself, we will form a compound that has a hydrated functional group, particularly hydroxyl, with your halo compound. So, they are vicinal to each other. Okay? So, again, for our features, remember, class, this is through anti-addition because you will form a halonium intermediate. And remember, your halogens here or your halide are bulky molecules. That's why they prefer anti-addition. For the first reaction, similar with halogenation. For the nucleophilic attack of water, similar with what we have seen in hydration. Okay? So class, more specifically, in halohydrin formation, backside attack can actually open the halonium ring, your intermediate, that will lead to your anti-addition. Remember, class, for anti-addition, we are regiospecific. So we will only form the trans product, diba? As we have discussed, cis for your syn addition, trans products for your anti-addition. As you can see here, because of the backside attack, we will form anti-products, or we also call it your trans products. Okay, so aside from that, with your asymmetrical alkenes, only one isomer forms as your water will add up or add to the more substituted carbon. Let's check the particular asymmetrical or unsymmetrical alkenes. So as you can see here, we have a certain reaction wherein we will use again class your halogen diatomic bromine for instance, and then hydration with water. So usually this is acid catalyzed halohydrin formation. Okay, so remember, this reaction is a follower of Markovnikov rule. That's why, of course, your hydrogen bonds to the more substituted C in our intermediate, okay? And aside from our typical reagent na bromine and water, actually class, are you familiar ba with your N-bromosuccinimide? Or we also call it your NBS, diba? Not National Bookstore, N-bromosuccinimide. This one is a board exam relevant topic class. Remember, we can also do halohydrin formation using your N-bromosuccinimide. Oh, sir, what's the relevance of your NBS? Class, this is our source of your bromine or halogen in general. So NBS in your aqueous DMSO can also form bromohydrines from alkenes by the same reaction mechanism. Class, again, I would like to clarify and point it out. We are specific to the production of bromohydrine. When you see NBS, that means n-bromosuccinimide. Automatic, you should have a bromine that is vicinal to your hydroxyl group. When we say vicinal, they are attached to adjacent carbons. And remember, we still follow the anti-addition. I hope it's clear, class. Remember, anti-addition is our process for halohydrin formation. Okay, again, required po sa DMSO in water for our n-bromosuccinimide halohydrin reaction. Okay, so class, last two for our electrophilic addition. Ayan, for our next reaction, oxymercuration, the mercuration, di ba? So here, we will use your mercury intermediate or not intermediate reagent, particularly that's your mercury acetate in your tetrahydrofuran solvent. Class, here, we will do your oxymercuration and demercuration individually. Okay, so alkene oxymercuration, as you can see here, is closely analogous to our halohydrin formation. So what's the reason? Here, instead of forming your halonium, bridged halonium intermediate, we will actually form your mercurinium ion. So it will resemble our bromonium intermediate. Okay, so again, this is an EA, electrophilic addition of your mercury 2 plus to our alkene. And class, remember, requirement po si aqueous THF. Okay, so for our particular reaction example here, for instance, we will now do oxymercuration first with our alkene example here. When the intermediate organomercury compound, so this one will insert to our alkene, okay, our alkene initial substrate. And then for the second reaction, we will do reduction. Or class, we also call this your demercuration reaction because we will induce, okay, the demercuration reaction through the introduction of your sodium borohydride. Class, remember, sodium borohydride is a reducing agent, okay? So again, nucleophilic addition of water will be done as in similar with your halohydrin formation, alright? So this will be followed by the loss of your proton. So class, don't worry, it's not needed for our board exam, but again, I'm just discussing it for our rationalization ng reaction mechanism. Again, for the second step, we use your sodium borohydride for the demercuration process. Okay, so again, this will involve a complex and radicals. So remember, class, we don't need to discuss that, but remember, the radiochemistry of our reaction here corresponds to your Markovnikov rule. Okay, so remember, the hydroxyl group that will come from your water will attach to your more highly substituted carbon. So here, class, this will be the point of attachment of our hydroxyl group. Okay, that's why our product, ayan, of course, this is a relatively more stable alcohol. Remember, this is your tertiary alcohol because your carbon here is attached to 3 different R group or carbon-containing R group. Clear ba tayo, class? Again, here in the laboratory, this is our main procedure in the hydration of alkenes. So what's the reason? Relatively easier to handle kasi class yung reagents natin. And of course, regio-specific siya. Okay? So class, for our specific reaction mechanism, ayan. So again, from our previous slides, we have your 1-methyl cyclopentene. So here, the electrophilic addition of your mercury 2 plus gives your mercurinium ion. Okay? So for our second reaction, your mercurinium ion will react with water. Also, what's the structure of your mercurinium ion? Class, again, this is a intermediate that is produced upon addition of your mercury acetate. Okay? So again, upon reaction, in our second step, we will now form our second intermediate. So here, loss of a proton will give our organomercury product. So as you can see here, class, this is our organomercury product. As you can see, naka-insert po si mercury inside our 2 different R groups. Alright? And for our third reaction, we need to demercurate our particular intermediate that is formed through the reaction of your sodium borohydride. And usually, class, again, it will follow your Markovnikov rule where your hydroxyl group will attach to a more substituted carbon. Okay, so again, that's our last reaction here. Markovnikov regio-specific book class. For our particular example, we will produce 1-methyl cyclopentanol. Okay, so that's it for our oxymercuration, demercuration. Class, again, this is a pretty straightforward reaction. From your alkene, or remember our strategy here, our point of attachment or hydration is in your more substituted carbon. Ganyan lang siya, class, ka-easy to predict. Okay, so no need to do arrow pushing if you know your Markovnikov rule. Alright, so remember, when you see your mercury acetate in your reagent, automatic, that's for hydration when it is followed by sodium borohydride. Alright, so class, last na lang po for our electrophilic addition, and that is your hydroboration oxidation. So here, we will use our complex BH3THF in order to form our bridge intermediate. Usually, class, tetrahydrofuran, this is our main solvent in our alkene reaction. Alright? And remember, for your hydroboration oxidation, diba, we discussed this in your anti-Markovnikov addition. Ayan, very unique siya because it will not follow. Diba, kasaway siya because it will do your anti-Markovnikov addition. And remember, class, it will not allow your rearrangement of our intermediate. But it will still undergo syn addition of our specific substituents here. Let's check. So class, here is our general mechanism. So as you can see, anti-Markovnikov, your hydroxyl group will attach to your less substituted carbon in our general reaction mechanism. That's it. That's our general tip. So sir, is that the opposite of your oxymercuration, demercuration? Yes. Diba, remember, for our previous reaction, oxymercuration, demercuration, your point of attachment of our hydroxyl group should be in this substituent. Diba? They switched up in their position of your hydroxyl group. Because, again, this is your non-Markovnikov hydroxyl addition. Class, usually we also call this your peroxide effect. Okay, for our step 1, again, we will form your boron intermediate. So as you can see here, hydroboration and hydroperoxide and ion formation is our step 1. And this one will occur individually, class. Okay, so again, it is important that we form your highly reactive intermediate in order to produce our stable or relatively stable boron organic compound. Let's check. for your hydroperoxide and ion formation class, actually this is very important because this will be the one or your nucleophile that will initiate the obstruction of your boron substituent here. Okay, BH2 will leave our organic compound via the reaction of your hydroperoxide and ion. And in turn, your oxygen now will be deprotonated. That's why at the last step class, of course, hindi na siya kita here, but our last step here is protonation of our single bonded oxygen to form our hydroxyl group. Because again, your oxygen will carry temporarily a negative charge. Class, again, our general tip here, your anti-Markovnikov or non-Markovnikov addition will add up your hydroxyl group at the less substituted carbon. Okay? So again, for our specific reaction here, let's just briefly discuss this. Again, BH3, in the laboratory, it is actually hard to handle. It is a reactive gas. Remember, in our laboratory, we have different reactive reagent as well. And usually, it exists as a di compound. And usually, class, in your solution, your BH3 or your boron hydride exists as its diborane counterpart. Because relatively, that's our spontaneous, okay? Spontaneous reaction of BH3 in order to form diborane. So for its in handling in the lab, usually it is complex again with your tetrahydrofuran. Let's check. Again, your DHF will act as a Lewis base in order to stabilize or to abstract our boron atom here. So your boron hydride will now act as your Lewis acid. See class, this system pala is an acid-base system. And in your solution, our boron hydride DHF complex will form this particular compound. That's why it is regioselective. Okay? So as we have seen in our previous slides, your unsymmetrical or asymmetrical alkenes, the boron atom will bond to your less substituted carbon. For this case, nandito siya class. Okay? So again class, remember, this will be our intermediate in your reaction and your only product upon formation of our reactive intermediate. Remember class, this is not our final product. Okay, so again, this one will be replaced by your hydroxyl group. This just shows how boron hydride is incorporated to our organic compound. Okay, ayan, that is your last substituted carbon. Okay, so that's it for our last electrophilic addition reaction of alkenes. Class, for our last discussion, let's also discuss hydrogenation. Remember, this is also unique for your alkenes. So this one class, we actually use here metal catalyst. So this one is a classic example of heterogeneous catalysis. So meaning, the phase of our reagent is not similar with the phase of our metal catalyst. Because usually class, yung hydrogen natin here is in gaseous state, while yung metal is actually in solid state. It acts as an anchor that will serve as a site of our hydrogenation. So again, for your hydrogenation, this is a catalytic addition, and this is distinct from electrophilic addition. Sir, bakit po? As it does not involve ionic intermediates or electrophiles. Class, actually straightforward yung reaction here. We will just add your hydrogen gas across the double bond in the presence of your metal catalyst. Check natin ha yung steps. First two steps, complexation of your hydrogen and the alkene to the catalyst. So of course, that's just immobilization of your two reactants in order to make your reaction highly specific. For the steps 3 and 4, ayan class, after immobilization, we can now sequentially add your hydrogen atom across the double bond. Sir, what is the specific type of addition? Syn or anti? Or check the structure of our product. Is it cis or trans? Again, for syn, cis ang product. For anti, trans po ang product. Class check, this is a cis product. That's why it occurs through syn addition. Clear? Ayan, so class, in order to visualize this clearly, let's watch this short animation on hydrogenation. Let's check ha.
Addition reactions of alkenes. The most important reactions of alkenes are addition reactions. One of the industrially significant examples of addition reaction is the hydrogenation reaction of vegetable oils, which contain unsaturated hydrocarbons having double bonds. In the presence of a nickel catalyst, hydrogen gets added onto the unsaturated hydrocarbons, and they are converted into saturated hydrocarbons. This reaction converts vegetable oils into margarine. For simplicity, we will study the hydrogenation reaction with the simplest unsaturated hydrocarbon, which is
Class, I'm sorry, ayan, na-reveal na pala. So anyways, again, for your hydrogenation in the industry, again, we usually use your metal catalyst. We have 3 important metal catalysts. You have your nickel, palladium, or platinum. Usually platinum yung ginagamit.
ethene molecule. This reaction proceeds through 4 different steps. Initially, ethene molecules are adsorbed on the surface of nickel. Adsorption increases the concentration of ethene on the surface of the catalyst, which helps in increasing the rate of the reaction. During adsorption, the double bond between carbon atoms breaks, and new bonds are formed between carbon and the surface of the catalyst. Addition reactions of alkenes. The most important reactions of alkenes are addition reactions. One of the industrially significant examples of addition reaction is the hydrogenation reaction of vegetable oils, which contain unsaturated hydrocarbons having double bonds. In the presence of a nickel catalyst, hydrogen gets added onto the unsaturated hydrocarbons, and they are converted into saturated hydrocarbons. This reaction converts vegetable oils into margarine. For simplicity, we will study the hydrogenation reaction with a simple.
So class, that's our transition state that occurs during hydrogenation. See, we do not form ionic or positively charged intermediates here. Here in our hydrogenation, we have the complexation process between your metal and our carbon atom. Let's continue.
Simultaneously, hydrogen molecules also get adsorbed onto the surface of nickel. Here, they get broken down into hydrogen atoms. These hydrogen atoms can move over the surface of nickel. Of these hydrogen atoms, the one which diffuses close to the original ethene molecule breaks the old bond between carbon and nickel, and a new bond between the carbon atom and hydrogen atom gets formed. The end of the original ethene where a new bond is formed now breaks free of a nickel surface, and eventually the other end also breaks free. Thus, the product ethane is now entirely free, and this leaves space on the surface of nickel to adsorb more ethene and hydrogen. Simultaneously, hydrogen molecules also get adsorbed onto the surface of nickel. Here, they get broken down into hydrogen atoms. These hydrogen atoms can move over the surface of nickel. Of these hydrogen atoms, the one which diffuses close to the original ethene molecule breaks the old bond between carbon and nickel, and a new bond between the carbon atom and hydrogen atom gets formed.
Class, that's it for our hydrogenation. Again, as you can see, the addition of hydrogen occurs through syn addition, meaning on the same side of our carbon atom. So that's it again for hydrogenation. And now we are done with our 6 different types. So class, hindi kasama si hydrogenation in your electrophilic addition ha. Again, that is a heterogeneous catalysis type of reaction of your alkene. So going back for electrophilic addition, let's have a recap. We are done with hydrohalogenation, halogenation, hydration, halohydrogen formation, and last 2, oxymercuration, demercuration, and finally, hydroboration, oxidation. Kaya pa. Class, you can take breaks during our discussion. Alright? Of course, very saturating ang alkene discussion natin. Don't worry for the alkynes. We are just going to emphasize those board exam relevant topics because in the board exam usually they focus on alkenes kasi. That's why we need to take our time in order to specifically discuss this particular reactions. Okay, so class, again, that's it for our electrophilic additions. So now, we will transition with our next type of reaction, your polymerization reaction. Class, again, when we say polymerization, we will condense your monomers. Okay, so this is a process in which your monomers, usually they are small molecules, such as your alkenes, will join or react with each other to form repeating chains of these monomers, and eventually we will call them polymers. And for alkene, remember this, they are forming your polymer through addition polymerization. So usual types of alkenes that are involved in your polymerization process include your, ayan class, diba? Polyethylene bottles, your polypropylene, polyvinyl chloride, and polystyrene. So these are the monomers of this 4 polymers class. And in our polymerization, usually, the pi bond that is present in your double bond. Recall in our discussion on hybridization, we have 1 pi bond present in our double bond. So this one will break, allowing each monomer to react with each other, and thereby linking covalently in order to form a saturated. Meaning class, we will convert the double bond simply to your single bonds to form our polymer. For our visualization again, we will now watch a very short animation on your polymerization process. So for this one class, this occurs through free radical polymerization. Again, the addition polymerization, typical reaction mechanism of course, will include free radical polymerization. Let's see.
As an example, the raw material used in the process is ethylene, which is the monomer in this case. While monomer means one part, polymer means many parts. So polyethylene basically means many ethylene parts. But how do we get from one part to many parts? It actually takes 3 steps. The first step in the polymerization process is the initiation. When heated, the organic peroxide breaks apart into radicals. These radicals start the reaction with ethylene. One free radical opens the double bond on an ethylene molecule and forms a new radical. Then this new radical opens another ethylene monomer, and this process continues, making the actual polymer. This second step is called the propagation. Now there's only one step to go to turn a monomer into a polymer, the termination. The polymerization reaction stops once the last radical on one polymer chain meets another chain with a free radical. Then they combine, and the polyethylene is finished. As an example, the raw material used in the process is ethylene, which is the monomer in this case. While monomer means one part, polymer means many parts. So polyethylene basically means many ethylene parts. But how do we get from one part to many parts? It actually takes 3 steps. The first step in the polymerization process is the initiation. When heated, the organic peroxide breaks apart into radicals. These radicals start the reaction with ethylene. One free radical opens the double bond.
Okay, so class, seems familiar, di ba, yung steps natin in your free radical polymerization. It somehow resembles the mechanism that your alkane halogenation adapts. Di ba, it also occurred in 3 steps. And for your free radical polymerization, again, we also have these 3 steps: initiation, propagation, and lastly, your termination. Okay, so class, simply for our initiation, this is where your free radical is generated coming from your hydrogen peroxide usually. Okay, so again, often your peroxide acts as an initiator. So we do not necessarily need here your light in order to induce your radical formation. Next, for our propagation, this step is particularly for chain elongation. As you can see, our reactants are your free radicals. And for your products that will create free radicals, ayan, this will become your sequential addition of free radicals with your alkenes in order to elongate your chain. O sir, kailan po mata-terminate yung free radical polymerization? So termination will occur when your radicals, particularly 2 radicals combined, we call it your deactivation or termination step. Okay? So again, usually class, this polymerization is widely used in your production of plastics, diba? Your polyethylene bottles, or polyethylene of course, or your synthetic rubbers and your pipes, polyvinyl chloride pipes. Okay? So for our typical alkenes that participate in polymerization class, we listed it down. We summarized those relevant alkenes for your reference. Again, some application include the synthesis of plastic. For styrofoam, diba? Polystyrene. And of course, we can also use your polyacrylics and your rubbers, synthetic rubbers. Clear ba class? So please read na lang this. I will assign it as a reading assignment. So usually in the boards naman, this does not appear. Kaya pa ba? Again, class, last set of reactions na lang for our alkenes. Remember, we also have your oxidation and cleavage reaction. This one, let's just enumerate first our 4 different reaction type. Firstly, we have your epoxidation. Sir, what's the reagent here? See, we have your MCPBA. And usually this is a syn addition. And we will also use your concerted reaction. Class, your alkene can actually our precursor molecule, for synthesis of epoxide. Later, we will discuss the specific mechanism for this reaction. But for now, again, your alkenes are highly reactive toward your hydroxylation. In particular, dihydroxylation due to the electron-rich nature of your double bond. Okay? And this is very important in transforming our alkenes to valuable organic compounds. Let's check. For dihydroxylation, we actually have 2 different mechanisms, syn or anti. Alright? So of course, for your dihydroxylation in syn conformation or syn addition, we usually use your potassium permanganate. Okay? So our product here, of course, class, di ba remember pag syn, cis. And for our dihydroxylation, we will form diol. Vicinal diol meaning your hydroxyl group are attached to your adjacent carbons. So similar yan class for your anti and syn dihydroxylation. So what's the difference? Again, for syn, cis product. For anti, we have your trans product, particularly transvicinal diol. Later, we will discuss the specific type of additions and mechanisms. But for now, class, again, I would like to emphasize the reagents. For your dihydroxylation, usually potassium permanganate or your OSO4. Okay? For anti-dihydroxylation, we have your MCPBA or your meta-chloroperoxybenzoic acid. Clear ba? for our DMS class, remember, ayan, this is used on your ozonolysis. So usually this is the cleavage of your carbon-carbon double bond. Class, this one is very easy to remember. Again, we will just simply cleave your double bond, and typically our products are aldehydes and or ketones. So I know it's very hard to visualize if you don't see our reaction mechanism. So let's now proceed with our discussion of your reaction mechanism here, starting with your epoxidation. Okay, so again, epoxidation, main reagent is your metachloroperoxybenzoic acid. So here is the structure of MCPBA class. Okay, so again, we have two consecutive oxygens attached in our carbon directly. And remember, our intermediate here will be your formation, of course, ng reactive triple or ring intermediate. Okay, particularly is a triple-membered or a three-membered cyclic ether. O, diba? That's your epoxide. So class, we don't necessarily need to discuss the reaction mechanism. But for the sake of our rationalization here, o, diba mahirap naman kung hindi natin i-discuss. That's why for our next slide, we will focus on how we arrive with your epoxide formation through the reaction with MCPBA. But remember here again, typical feature, concerted mechanism, and scene addition. And because of that, the stereochemistry will be retained. O sir, what's the reason? Again class, because of your concerted mechanism. Okay? So remember when we say scene addition, your O or oxygen will attach to your same side of our carbonyl, carbon-carbon double bond. Let's check our reaction mechanism here. For epoxidation, again, all bonds are broken or formed in a single step. Class, that's literally the definition of your concerted mechanism. And particularly, the oxygen-oxygen double bond, ayan, in your MCPBA will be broken. As you can see here in our reaction mechanism, let's start with the initiation of your electron-rich attack of your carbon-carbon double bond. As you can see here, when your electron-rich double bond initiate an attack, this will lead to the cleavage of your oxygen-oxygen double bond. And simultaneously, the oxygen that was attacked by your electron-rich double bond will also attack the carbon. O sir, yan po ba yung formation ng triple-membered ring or three-membered ring? Yes. And finally, in order to get your proton, your carbonyl carbon or your carbonyl functional group will abstract the proton. And our final product, of course, this is your carboxylic acid as your byproduct in epoxide. Okay? So remember class, epoxidation from the name of the reaction itself, please remember our product and the reagent. Epoxide product, MCPBA reagent. So for per acid compounds, they usually have your oxygen that are directly bonded both to your carbon. So here we have your COOH, single bonded oxygen-oxygen bond. So usually class, mabibreak po to in our epoxidation reaction. Next. With our dihydroxylation reaction, remember, we use two different reagents here. But class, either way, we will generate your cis intermediate. Let's proceed with our discussion ng typical reaction for our dihydroxylation. Again, this is your syn and anti-dihydroxylation. This one, anti-product because your hydroxyl group are trans to each other. This one, very obvious, they are cis to each other. Okay, so class, for our next slide, let's check the typical mechanism of your syn hydroxylation first. Ayan. So for anti kasi usually, similar lang po siya sa epoxidation because MCPBA again will first provide or form epoxide intermediate, and then for your protonation, you will break now the epoxide in order to form the diol product. Let's check our syn hydroxylation. Class, for your syn dihydroxylation, your permanganate and your osmium tetroxide will just have the same mechanism. Okay? As you can see here, remember, your oxygen are relatively electronegative. So the point of attack of your double bond will be our oxygen here because polar bond po yan. Okay? So somehow it carries your partial positive charge because of the delocalization of your double bond here. And consequently, for the other oxygen atom bonded to your manganese, okay? Manganese center, you will initiate an attack to the other carbon double bonded to another carbon. Similar lang class again for your osmium tetroxide. And because of that, we will form your complex here, your alkene and your permanganate or your osmium tetroxide complex. And in order to convert and to break these bonds, see, we need to do hydration. Remember class, this is a polar bond. So that's why favorable na i-cleave natin through hydration process. So for your syn dihydroxylation, your hydrogen or your water will add up your hydrogen at the same side. Okay? So remember our product is this 1,2-diol, particularly vicinal diol. Class, that's it again for our dihydroxylation. Lastly, with our ozonolysis, again, this one is just a simple cleavage of your double bond. So that's why we will form two products. So literally, this is an oxidative cleavage using your ozone gas. So again, your alkene will break both the pi and sigma bonds of our carbon-carbon double bond to form two new carbonyl functional group. Class, depending on the number of the R groups. For instance, in this carbon, we have two R groups, but in our right carbon, we only have one R group. So usually, we will produce ketones if you have two R groups bonded to your carbon. But class, pag isa lang po, recall, this is a typical structure of your aldehyde. So that's why this is our product, either your ketone or your aldehyde, again, depending on the number of R groups. Let's check our particular example here. Class, again, very easy to predict to. Cut the double bond and then add O to our carbonyl carbon. Okay? That's why, ayan, our product will be your ketone and aldehyde as well. Okay, remember, reliant po yan sa number of R groups. For our typical reaction mechanism, usually this occurs through your cyclic intermediate before we cleave our final product or to form our final product. So ozone kasi will add to your alkenes that will form a very unstable. When we say unstable, it carries high amount of energy. So this is your molozonide intermediate. So this one class will be converted or rearranged to ozonides. So their difference is just the bonding of your oxygen. Here, your 3 oxygen, due to your complexation with your ozone or the attack of your ozone, will form your molozonide. And upon rearrangement, you will form a more highly reactive intermediate ozonides that will be cleaved to your aldehyde or ketones class. Okay? So check nyo po yung arrow pushing mechanism. Ang first to attack here is the oxygen that will attack our carbonyl, not carbonyl, your carbon-carbon double bond, and consequently again, this will also attack your another oxygen. Remember class, your oxygen center here in your ozone, it has a resonance structure. That's why the oxygen center will carry a partially positive charge. And because of that, very favorable ang formation ng cyclic intermediate and highly reactive intermediate that will be rearranged to ozonides. So usually po, ang ginagamit to cleave is a zinc metal. Okay? In your dimethyl sulfide, solvent. And remember, depending on the R group, our product is or are aldehyde and ketones po. For our final discussion on ozonolysis, let's watch this short animation on how ozonolysis works. So this one is particular for ethene. So remember, ethene, it contains 2 carbon atoms. So ako na lang yung mag-class ha, wala kasing sound yung video. First, again, the formation of your malozonide through ozone addition. Class, again, this oxygen has a partially positive charge. And as you can see, this is a concerted reaction wherein your mol ozonide will form. So no worries class ha, you don't need to memorize our structure here. Ayan, formation of malozonide, our highly unstable and energetic intermediate. So next step, as we have seen in our previous slides, rearrangement lang po ng oxygen atom for preparation sa cleavage reaction. Let's see, medyo mabagal yung video. Check, because this one is a more favorable intermediate for cleavage class. That's why we need to rearrange it. And ozonide in the presence of your zinc metal dust with water will form formaldehyde. Sir General yun, formaldehyde, no class for ethene lang. Remember, ethene simply 2 carbons with its substituents, hydrogen atoms lang po. Okay? That's it for our ozonolysis. Class, for our supplementary or special topic for alkenes, we will also discuss your color conjugation. Okay? So again, the capability of your compounds to absorb light is because of the conjugation of double bonds. Okay? So again, these are our typical conjugated alkenes. So molecules having 8 or more conjugated pi bonds present in your double bond can absorb in the visible region. And because of that, this compound can take the color of those wavelengths of your visible light that it does not absorb. Diba remember? An example of your compound with extensive conjugation, we have your lycopene. Ayan, it absorbs visible light, I think around 470 nanometers. So that's in the blue-green region. That's why it does not absorb the red region because your lycopene appears red. Diba class, again, that's your complementary colors in your color wheel. Remember, your lycopene again absorbs at the blue-green region, thus it does not absorb the red region, so usually it appears red. So this is the typical fruits and veggies that have lycopene as its main component. Okay? So again, for our special topic, let's discuss color conjugation.
This spectacle test began with tomato juice and is called the tomato juice rainbow. How do we create this fantastic rainbow using tomatoes? Keep watching. First, we make bromine water. Quite simply, this is molecular bromine dissolved in water. Then we inject the bromine water onto the tomato juice to initiate this colorful effect. Because tomato juice is so thick, it helps the reaction last much longer. The long narrow test tube keeps the color separated longer by maintaining a steep density gradient. If we compare it to a shallow beaker, the colors mix rapidly to look more like a tomato juice swarm. Tomatoes are red because they have the guanide lycopene, which absorbs green light. When we add bromine water to the tomato juice, it adds to the lycopene and it removes double bonds in the molecule, which means it absorbs a shorter wavelength of light. This explains why we see yellow, but not always see blue and green. These intriguing blue and green layers are from the stage just before bromine adds to lycopene, called the charge transfer complex, which allows the exchange of charges between the bromine and the double bond. We see blue because the charge transfer complex absorbs light at higher wavelengths, and when the blue and yellow layers mix, we get green. That's all for this episode of Chemlabs. Make sure to check out the original publication in the Journal of Chemical Education so you can show off this demo to your students.
Diba class, amazing. Actually, when I first read about your tomato juice rainbow experiment, so I have somehow a brief idea about the mechanism behind. So remember, ang conjugation po ng double bonds, it's still reactive. So for your bromine atoms or your diatomic bromine, again, it can add up through halogenation. So that's why, remember, you need to familiarize yourselves with the color wheel with your tomato juice rainbow experiment. Class, don't worry, this one naman, it does not appear in the boards usually. So again, special topic lang siya for our discussion ng conjugated dienes. So typical example again ng conjugated dienes are your lycopene because we have the presence of numerous double bonds, alternating single and double bonds in particular. Okay? So this alternating structure of single and double bonds actually may affect po siya sa behavior ng conjugated dienes. Okay? So particularly sa chemical reactivity niya. So here is our typical structure ng conjugated dienes, particularly with our unhybridized p orbital. See again, this one has an effect in the behavior or the chemical reactivity of your conjugated dienes. So because of this resonance stabilization of your double bonds, again, we will form allylic carbocation intermediate usually in the reaction. Let's just first enumerate the typical feature or structural features of our conjugated dienes. First one, a conjugated diene is stable because of overlapping p orbitals on 4 adjacent atoms. Class, usually ang prominent example ng conjugated dienes are your 1,3-butadiene. This is literally the structure of 1,3-butadiene. So the central carbon-to-carbon single bond is usually shorter than your typical single bonds. So what's the reason nga again? Because of the resonance of your double bonds in our structure ng conjugated dienes. Again, class, somehow meron tayong very little or small amount of overlap ng pi bonds. That's why ang reaction or single bonds natin here, meron silang partial double bond character. So actually lahat nga here merong partial double bond character upon resonance stabilization ng structure ng dienes. So for the electrophilic addition in your conjugated dienes, usually we use your HX compounds. So usually HCl or HBr. Let's check the typical reaction of conjugated diene electrophilic addition of your HBr or HX in general. Let's see. For your conjugated diene, your double bond will obstruct a proton, leaving your bromide ion. For our intermediate class, because again, remember this is your allylic carbocation because the carbon that carries the positive charge is directly bonded to your carbon that is doubly bonded to another R group. So this one can actually have resonance forms. So they can interchange or stabilize through the localization of the double bond. Okay? So again, both of our intermediate are allylic carbocation. Class, for our reactions ng conjugated diene, actually meron tayong two products. The kinetic, which will be the first to be produced, and the thermodynamic product, which is relatively the more stable product, but very slow ang reaction yan. Okay, again, kinetic, fast reaction, but relatively less stable. Si thermodynamic, more stable, but slow step po siya. Again, it forms very slowly. Let's discuss. Ayan, for our 0 degrees Celsius and at 0 degrees Celsius, we will form your kinetic product. So usually, that's just your first intermediate. We will form the 1,2 addition product. O sure, but 1,2. Remember class, again, in terms of our numbering, we will use or prioritize your C1, and then this is your C2. And that's why we will form the 1,2 addition product. Okay, again, this is formed faster because again, kinetic product siya. Relatively less stable. Next. At 40 degrees Celsius, 85% is formed via the thermodynamic reactions. Here, class, ayan, nagkakaroon na ng resonance stabilization. Here, this is your 1,4 addition product because you will add your H at the C1 but your Br at your C4 carbon. Okay? Again, forms lower or C, thermodynamic product. Class, let's summarize. For your 1,2 addition product again, your hydrogen is added to C1, your bromine is added to your C2. Again, we will prioritize numbering our initiator of your attack or obstruction ng proton. Okay? Class, remember it ha, your C1 is always the one that initiates the attack. That's why, for our first intermediate, usually nandyan yan sa nearby carbon with your positively charged carbon. Okay? Second, for thermodynamic product again, because of the resonance stabilization of your allylic carbocation, you will form 1,4 addition product. Literally, the H will be added at the C1, but the Br is at your C4. O, diba? Magkalayo sila, class. So, in order to test your knowledge, let's try answering our sample problems here on the formation of your kinetic and thermodynamic product. O, please pause the video. Again, predict the major products from the reactions of our conjugated diene. So, please label the kinetic and thermodynamic products. Okay? Class, please again pause the video, but for now, I will discuss the answer. Or remember, our first product kinetic, of course, this is your C1. It will initiate an attack, so that will add your hydrogen. Okay? So again, for your 1,2 addition, this is your C1, this is the C2. So class, dito po dapat magbabind si Br, sorry, OMG, ayan, dito po magbabind si Br, and dito mag-a-attack si H, or your electrophilic H will be added at your C1 position. Okay? Our kinetic is this one. For thermodynamic, again, meron tayong rearrangement that will occur. So for the C4, di ba? 1,4 addition product. So dito pa rin po, si H magbabond. But for the C4, again, C1, C2, C3, C4. O sir, dito ba siya magbabond? Yes. Because, again, class, this will form your resonance, stabilized, positively charged, allylic carbocation. Okay? So I hope it's clear. Ayan, that is your thermodynamic product. Okay? For our second sample problem, class, again here, we have your asymmetrical conjugated diene. So in this case, you will prioritize your 1,2 product that will form a more stable carbocation. So with that being said, class, we will treat this particular carbon as our C1. Ayan, so C1, C2, C3, and C4. So firstly, kinetic product, again, don't forget, C1 and C2. Specifically, this will be our proton obstruction in C1, while Cl will attack our formed carbocation upon addition of water. I'm sorry, of your hydrogen. Alright? So class, for our 1,2 kinetic product, this should be your answer. So no rearrangement of double bond will occur. Again, our C2 will form the highly stable carbocation. Tertiary na siya, allylic pa siya. Alright? So for our thermodynamic product, 1,4 addition. So similarly, class, this will be the point of attachment of our hydrogen. But we will have a rearrangement of the double bond between your C2 and C3, and finally, ayan, si chlorine po will bond on this particular C4 carbon. So for here, your answer should be in this type of structure. Your double bond migrated between our C2 and C3 position. So that's it for our discussion on conjugated diene. And with that, we now arrive with our final Lars words. Ayan. Ayan. So class, again, for our Lars words for alkene, don't forget, its structural feature, double bonds, and this double bonds will adapt sp2 hybridized orbital, and consequently, geometry planar with a bond angle of around 120 degrees apart from each other. For our formula, remember, we have 1:2 ratio for our carbon and hydrogens found in our alkenes. Now, for geometric isomerism, remember class, cis trans identical atoms easily use your rules due to the restricted rotation across our bonds. So remember, geometric isomerism is exclusive for carbons that have restricted rotation. And don't forget, naming or nomenclature, we use your suffix "ene," ene if we will prioritize your alkene as our functional group. So additionally, boiling point, slightly lower than alkanes because of the tight tapping of the structure of your corresponding alkenes with similar number of carbons. For solubility, remember class, we already generalized this, water insoluble and soluble in nonpolar solvents for all hydrocarbons. And for reactivity, remember, its characteristic reactivity is electrophilic addition across the double bond. Alright, for our key feature, so set us first, sorry, when your electrophile is added to more substituted carbon, Markovnikov or anti-Markovnikov. Again, your electrophile will be the first one to be added. So if it's in your more substituted carbon, anti-Markovnikov. So if it's in your less substituted carbon, clearly, that's our Markovnikov addition. And lastly, for our sine and anti-addition, sine, same side, while anti, opposite sides. Alright. For our summary ng reactions ng alkenes, we provided you a summary of the very relevant reactions of alkenes. So we discussed all of these reactions. Firstly, this is your hydrohalogenation. Here are the reagents. Again, it corresponds to our product. Next, this is your halogenation. This is your, plus what is this? Oxymercuration, demercuration. Next one, ayan, when you use alcohol instead of your water, again, similar mechanism with your oxymercuration, demercuration, but here, instead of alcohol, we will form ether po. Clear ba? Again, we just use alcohol instead of water. Next, you have your hydrogen formation. And then, of course, for our sixth reaction, that is your hydroboration oxidation, the only non-Markovnikov or anti-Markovnikov reaction. 7, we have your hydrogenation to convert your alkene to alkanes. 8, what's that? Oxidation. 9, we have your hydroxylation or dihydroxylation. 10, we have your ozonolysis. And this one, class, we did not discuss this, so supplementary cyclopropanation. So this is particular with your alkene, particularly your 2 carbon containing alkene. Okay, this one will include your zinc copper. Okay, zinc copper reagent, and of course, usually in chloroform, your CHCl3 in your base catalyzed cyclopropanation. Okay, so that's it for our Lars words. And to wrap up our discussion on alkenes, class, let's have our new press here. True or false naman po tayo for this edition. Okay, first item, alkenes are more reactive than alkanes. Class, kung hindi pa naman to obvious, di ba naumay na nga kayo sa numerous reactions sa alkenes? This is true. Remember, through electrophilic addition. Class, please pause the video in order to try answering or guessing our quick quest items here. Next. Alkenes can be turned into alkanes by reacting with hydrogen and the metal catalyst. Is this true? Class, this is true. Again, this is your heterogeneous catalysis via the use of your typical metals. Again, nickel, platinum, palladium. This is your hydrogenation reaction. Okay? I hope it's clear. Class, please revisit our discussion if you are confused in our hydrogenation reaction. Next, in hydroboration oxidation, the hydroxyl group ends up on the more substituted carbon. Is that true? Again, kapag more substituted, this is your Markovnikov rule. Remember, si hydroboration oxidation is the only electrophilic addition that does not follow Markovnikov rule. Okay? So for your anti-Markovnikov reaction, dapat po less substituted carbon ang addition ng hydroxyl group. Clear? Okay, next. Halogenation of alkenes produces only syn addition compounds or products. Class, again, we discussed, I emphasize this. Halogenation, you will use your diatomic halogen, and they are bulky molecules. They prefer anti-addition to prevent steric hindrance. Okay? This is a false statement. It should be anti-addition. And lastly, we have about ozonolysis. Ozonolysis breaks the double bond and gives to carbonyl compounds. Is this true? Obviously, class, this is true. But remember, we can either form aldehydes or ketones depending on the number of our group. So this one is very, very true. Okay, so that's it for our discussion on alkenes. So for now, class, I will cut first the video for our part 2 discussion on Crash Course 3, sorry. We will now proceed with our alkynes. So don't worry, relatively shorter discussion na lang po yun because your alkenes and alkynes share the similar reactions due to the reactivity of double bond and triple bond for alkenes and alkynes respectively. Alright, so that's it muna class for our edition or for our part 1 video for Crash Course 3. Bye class!